Hello everybody, welcome to installment 2 in this Rocket Science 101 series. Today I thought I would just give a brief overview on some of the basic math skills you'll need for this series. Now, if you're a math whiz and have taken several calculus courses and know your stuff, skip over this video because it's going to be old hat to you. But maybe you opened up this book if you got it and noticed on the first page, oh, there's math. Wow, what is this stuff? Watch this video. So, the first thing I'm going to go over is some basic calculus. There are two main aspects of calculus. There are derivatives, and there are integrals. And they're basically two sides of the same coin. So let's talk about derivatives. A derivative is the slope of a graph. Now you might be thinking, wait a second, I learned that in Algebra 1. We all know what y equals mx plus b is. The slope is just change in y over change in x. And then we have y equals mx plus b. And yeah, that's all well and good, but what if you have a graph that looks something like this? What's the slope at that point? Well, you could try and take the slope between 2 points and do that, but a better approximation would be like that and that point and that point, and finally we get the tangent line, which is the line that touches at just one point, the point we're interested in, and that's the derivative. Now, how do you find that point? Well, this is where people usually introduce the concept of limits. Limits are basically just used to describe derivatives, and they're not usually used to actually calculate them. But so here you have a graph of, let's say, this is f of x. And so you want to calculate the derivative at point A, but to do that you go out to point A plus change in x, and then you have the function at these 2 points, f of a and f of a plus delta x. Now the limit, the derivative, the slope at just that point would be the change in y over the change in x as this change in x approaches 0. And you would write that like this: limit as delta x approaches 0 of change in y, which is f of a plus delta x minus f of a, divided by the change in x, which is a plus delta x minus a. And voila. There are two ways to represent symbolically a derivative. There's the function way, so the derivative of f of x is f prime of x. That's how you pronounce that. It's like a little apostrophe. And otherwise, the derivative of y is dy dx. Now, way back when calculus was being invented, it was basically discovered by two people simultaneously, separately too. They were Isaac Newton and some guy named Leibniz. I think Newton tended to use this way to represent his derivatives, and Leibniz used this way, if I'm not mistaken, which I might be. But that was just a little FYI. Now, you don't use the limit to actually calculate the slope at any point, because that would be a little bit time consuming. There are many rules that you just memorize how to do this, such as if you have x to a power, the derivative of x to a power is equal to that power times x to the power less than that power. So n minus 1. N times x to the n minus 1. And that's just something that you just memorize. Now what if you have a constant times that? So the derivative of a constant times any function is just the constant times the derivative of that function. So the constant just stays with it. What about the derivative of just a constant? That equals 0. Whoops. Because, well, that's like saying equals the derivative of c times x to the 0. So we would do 0 times c times x to the minus 1. Well, this is 0 times all this, so 0. Anyway, moving right along, let's talk about some more advanced functions like trig and stuff like that. Well, there's the exponential function, e to the x, and this is actually equal to e to the x. It's as simple as that. The derivative of e to the x is e to the x. And if you didn't know, e is a magic number that is equal to 2.718 or so, etc. It's like pi. It's irrational. It goes on forever. Some trig ones. The derivative of sine is equal to cosine of x. And the derivative of cosine of x is equal to negative sine of x. If you are unsure as to how to remember which is which, a really goofy way to remember is that sine looks like sin, and sin is bad, it's negative, so that's why this one is negative. That's just a weird way to remember that. Now, some more general rules, such as product rule. It talks about the derivative of two functions that are multiplied together. And this equals the derivative of the first times the second plus the first times the derivative of the second. And an easy way to remember this is just because it sounds nice. F prime g plus f g prime. F prime g plus f g prime. Another one is the chain rule. And this is about what if you have a function inside of a function, like f of g of x, and that would be the derivative of the outside function times the derivative of the inside function. So an example of this, let's say we have the derivative of sine of x squared, and that would be derivative of the outside is cosine times the derivative of the inside, which is 2x. So it's as easy as that. I guess that's all I want to talk about derivatives for now. There are lots of little rules that you just have to memorize. But now let's talk about the other aspect of calculus, which is integrals. In short, an integral is the area under a curve. So, to represent this pictorially, let's say we have a function that looks like that, f of x. What if we want to calculate the area between point A and point B? What is this area? Well, this area equals the integral from A to B, and that's the sign that represents an integral. It looks like an elongated S, times the integral of the function times dx. And dx is an infinitesimally small change in x. Now, where does this come from? Well, if you were to take a rough estimate of what that area would be, you would probably do something like this. You would say, well, I know how to calculate the area of a rectangle, so why don't I just take a bunch of rectangles like this and just sum them all up. That makes it easy, right? This width is dx, and this height is f of x. So the area of this one here would be dx times f of x. Just sum them all up. This sign here represents the sum of something, so the sum from A to B of f of x times delta x. And if we change delta x to very, very small, we get dx. So it's infinitely skinny, and then we have a perfect representation of this area. And so that directly relates to f of x times dx. So that's where the integral comes from. Let's talk about how to actually calculate an integral. It turns out that the integral is the exact opposite of a derivative. You have a function, and if you differentiate it, you get f prime of x, and if you take the integral of this, you get f of x. So this is derivative, and this is integral. So basically, as a brief example, say you take the derivative of x squared, you get 2x, and then you take the integral of 2x, and you get x squared. That's the easiest way I can explain it. So you basically reverse the differentiation rules, and that's how you take an integral. And that's for an indefinite integral, meaning that we don't have specific defined points that we're taking it between. We're just expressing this as a function, and then we it's basically from 0 to x. That's an indefinite integral. So you understand? I hope you do, because I'm not going over it anymore, because we are moving on to vectors. Okay, so let's talk about vectors and basic trigonometry that goes with them. Vectors have a magnitude and a direction. So the magnitude is basically like a length, and the direction is where it's pointed at. So the way we would draw a vector, say on an xy coordinate system here, it goes from the origin to some point out here, and it's an arrow. This has length, let's say maybe 6 inches, and a direction 30 degrees north of the x-axis. So vectors can be added, subtracted, and kind of multiplied in 2 different ways. So here are some basic vector operations. For u, vector u and vector v. And this is how you would denote it, either with like some sort of arrow on top, or in some textbooks they'll make it bold-faced, but it's hard to write it that way. So we usually put an arrow on top when we're writing it on paper. Okay, so how would you do vector addition? Well, u plus v, let's say this is vector u and this is vector v. To add them, you would just put one on top of the other like that. And then it goes from tail to tip, and that's your addition right there. What about subtracting them? Well, that just flips the direction of the second vector here. It's still pointed in the same way, just opposite. So that would be u minus v. This is u plus v. So now, let's move on. How would we better represent these vectors? How about as a sum of their horizontal and vertical components, right? Because if we take this vector plus this vector, we get our original vector. So now, if just applying basic trig, this horizontal component here would be 6 cosine 30, right? Because it's in the x direction. So vector v here is equal to 6 cosine 30, and as a multiple of the unit vector in the I direction, in the x direction, we call that I hat or whatever. And then plus 6 sine 30 for the vertical direction, and the unit vector in the vertical direction is j. I don't like to work with these i's and j's, even though most people do. I like to put vectors in these kind of square parentheses like this, and just write them like that. That's how I work better. Now let's talk about some kinds of vector multiplication. There are 2 kinds of vector multiplication. There's the scalar product, also known as dot product. The result is a scalar. It's just a number. It's not a vector. And for that we would do v dot u. And that's basically the 2 x components plus the 2 y components. The x components multiplied together plus the y components multiplied together. And you see how that's a number. Now, what is that exactly? What are we actually doing? Well, say we have 2 vectors, v and u. That's taking one projected onto the other, and it's that length from there to there. And I guess I'm not prepared to explain why that's useful at this time, but it is useful. Just take my word for it. And then there's the vector product, also known as the cross product, and that's denoted with the multiplication sign. And this yields a vector. Now, what exactly does this do? How do we come to that? Well, we take the I, j, and k unit vectors, the first vector, and the second vector, and we take the determinant of that, which will end up yielding v2 u3 minus u2 v3 u1 v3 minus v1 u3 v1 u2 minus u1 v2. And what is this? Well, basically this is a vector pointing in the plane perpendicular to the plane that the two vectors v and u are in. Why is this useful? Once again, I guess I can't explain it at this time, but it's used in physics, and I'm sure we will use it later on in this series. And it will become apparent then. But for now, just know that these exist and that they're useful. And you should know how to calculate them. So that's basic vectors. Let's see, what else do I need to talk about vectors? Well, what kinds of vectors do we have? Well, we'll be dealing with forces a lot. And we'll be dealing with velocity, not speed. Speed is a scalar, velocity is a vector. And we'll be dealing with, well, acceleration is sometimes a vector. We'll be dealing with these a lot in our rocket science studies. So it's good to be able to handle vectors, because when working with these topics here, we use vectors all the time. So that's basically all I wanted to talk to you about math skills that you need to know. I hope you learned something, and I hope you're better prepared for what's to come next. In our next video, we will be talking about, we'll be talking about physics in the next video. So I hope you learned something in this brief review of basic mathematics that you'll need to know. And I hope you'll not be scared off from the rest of the series, which builds on these skills. So, stay tuned for the more exciting parts of rocket science.